Okay, hi. I'm Tobias. I work at Imagination. I'll be here to talk to you about synchronization today. I've somehow managed to get quite involved with how synchronization works. I ended up rewriting basically the entire chapter with help from many others, but if you have any questions about synchronization at all, I'm probably your go-to guide today. So, synchronization, let's have a look at it. As app developers, you have a bunch of draw calls, and your aim is you want to get them from the GPU, and the GPU is ready, sat waiting for you to give it draw calls. And if you keep feeding it draw calls, it'll keep putting pixels out onto your screen, which is great. Except with Vulkan, you can easily go wrong. So when I say talk about keeping it fed, GPU needs a constant supply of stuff to do. Otherwise, it's going to go idle, stall. You don't really want to wait for the CPU to be trying to generate more work or for memory latency whilst you wait for something to be fetched from memory. Luckily, draw calls in and of themselves are quite good. They've got a variety of different work. There's vertex work, possibly tessellation, and geometry work, and fragment stage work usually. And all of this is pipelined in a modern GPU, so you get quite a lot of overlap naturally. But you still have to do some work to ensure that it actually happens. In GL, you just sort of did draw, and magically they would happen on the GPU, whereas in Vulkan, you sort of have to take a little bit of thought behind it. A very naive approach might be something like you generate a bunch of draw commands on your CPU and submit them to the GPU, and then wait for them to come back. If you do that, you're going to get big stalls on each processor as you wait for the other one. Whereas I'm hoping what most applications are doing is this, whereby you just submit some draw calls to your GPU, and then without even waiting, you just start doing the next frame, and then the GPU just gets on with it in parallel. The same sort of thing occurs on the GPU rather. So just taking the simple example of vertex and fragment shading, you don't want each draw call to wait for the last draw call to complete. You would like it, ideally, the fastest way to get it done is if each one is doing a little bit of work in parallel with the other one. So this is what I mean by pipelining, the idea of having stuff going on in parallel, but it's the last bit of the previous stage, for instance. So when I say not getting bitten, on the other hand, there's a lot of resources to deal with when you're drawing something. There's uniform buffers, vertex buffers, textures, any other number of buffers or images you're using. And it's quite important to make sure that whilst the GPU is accessing these, you don't mess around with it. You don't want to change the data whilst the GPU is accessing it. If you do, you don't know what value is going to come out. And even more important is to not delete things while the GPU is trying to use them, because then all sort of manner of things can go wrong. The worst thing about synchronization bugs is that they can do nothing. It's highly likely, particularly in Vulkan with all the controls, that if you do something wrong, there's a good chance nothing will happen. You won't track it down for a very long time, until one of your users complains about, oh, there's some weird tearing artifacts going on. Even within internal development, we're seeing this sort of thing where we've had an app running fine, and all of a sudden a new platform comes along, and it's like, what's going wrong? And we have to sit and debug it. It can even be worse than that. You might get image corruption, or everything might just blow up, and you're left with nothing. Which is obviously, at least you know something's gone wrong, I suppose, in that case. So I guess let's have a look at what you need to do in Vulkan to avoid this sort of thing. So first I'll go through a little bit of terminology for you, just so that when I'm saying these things, it doesn't just go over your head. The first simple one, an operation, pretty generic term. It just means something that can be executed on the GPU. Could be an entire draw call, could be a whole command buffer, it could be as simple as a single SPIR-V instruction, it could be anything. And an execution dependency is something that means one set of those operations is waiting on another set of operations to complete before it starts. So there's a synchronization point. On the memory side, and this is something that Vulkan is much more explicit than GL was, I'm going to be talking about something called memory spaces. This is a semi-arbitrary terminology that I've been floating around for a little while now, but what it basically means is either a piece of memory or registers or a cache. It's basically somewhere that data values can exist. And then a write propagation is a type of operation that can move data between those. So a flush or an invalidate would count, for instance. And then finally, a memory dependency is just it's just an execution dependency that includes write propagations, which is just a useful thing to keep in mind. So memory spaces, they're not too scary. There's a sort of hierarchical memory model in Vulkan. It's not very well written down right now. It's better than it was, but I'm working on it. But the idea is that you've got these sort of three areas. At the very top level, you have what is device memory, which is where you allocate your VK device memory objects. And that's sort of analogous to VRAM, if you want to think in those terms. And then below that, you've got your sort of cache levels. These are typically what pipeline barriers and events most of the fine-grained synchronization I'll be talking about will operate on. And at the very bottom, you've got the processor registers. So you've got your CPU registers, your vertex shader has its own register space, your fragment shader has its own register space. It is probably worth pointing out the device visible is actually way more complicated than a single block, but for the purposes of this presentation, I'll just treat it roughly as such. So if I take a look at sort of how you would do a write to get some data from a CPU to a fragment shader, for instance. So if I do a write on the CPU, this is going to be to a memory pointer. For simplicity, let's consider you've allocated a buffer and you've mapped the memory for that buffer, and that's what you've just written a piece of data to, a D-word or whatever it is you want. That write, at the point you do that, will exist in the processor register on the CPU, whatever the host CPU model is. If it's C++11, it's that, wherever that may be. In order to get it to this host visible stage, you have to either use the VK flush map memory ranges command or the coherent bit. So you'll note that as I'm passing this down, there is a slightly thicker arrow line with an arrow on the top of it. That indicates the direction that it's going to be pushed. Whenever you write something anywhere, it can, at any time and without warning, move to another memory space that's vertically adjacent. So you can kind of think about this in terms of a cache, which I've stopped here. A cache could flush its values at any time if something else has evicted it from the cache. And this is true for all of the memory spaces. So let's have a look at what happens if I also write to the same memory location in the same buffer in the same place from the fragment shader at the same time without any synchronization. So I've written in the fragment shader, and I haven't done any synchronization, but it's propagated to the cache. Now, there's a contention here. If I haven't put any synchronization down, there's nothing to guarantee whether write 1 or write 0 will hit that device memory first, and you end up with an undefined value. And what's worse, because anything can propagate at any time, and that counts as a new write, it basically means it's undefined everywhere as soon as you've done that. It's possible to correct this if you do manage to trip up on it, but realistically, you shouldn't be writing an app that could ever get into this state anyway. So this time, let's try it again, but we'll add memory dependency in. So I won't do the whole thing, but this time what we're going to do is we're going to guarantee that these writes are propagated. So you can't necessarily, although I talked about a flush command, you don't really force a cache to flush out or whatever. What you actually do is you guarantee that something has happened, which is a little strange concept to get around, but it's how you express synchronization. So the idea is I make sure I guarantee that all those write propagations have happened all the way up to where I'm going to write my second value. And that's important because that's the only way to guarantee there's no outstanding propagations that could happen and interfere with your work. Once something's been propagated once, it will stay there and it won't start doing it again. So it sort of is like sanitizing the path from one memory space to another. So if I've got a memory dependency that guarantees it gets all the way there before I start executing my writes in my fragment shader, then it's completely safe. Everything will go on and writes, and then again, if I get that all the way back up to the host, I can then start writing from the host again as long as I can guarantee that. So how do you do that? Synchronization primitives. There's a lot of them in Vulkan. There's three sort of broad categories I put things into with explicit synchronization. There is some implicit as well, which I'll cover at the end. The first sort of type is the fine-grained synchronization. There's a bunch of stuff you can do within a queue with quite fine granularity with very tight control over what actually happens when you do it. And then there's two other levels, semaphores and fences, which are a lot more coarse. But I'll start with the fine-grained because it's easy to describe the coarse stuff in terms of the fine-grained stuff. So the first and possibly most straightforward of those is the pipeline barrier. This basically, you define a precise set of pipeline stages for it, and which says the say, fragment and vertex stage from my previous Draw calls will synchronize with the compute stage in my next dispatch calls, something like that. You say the precise shader stages and fixed function stages that you're trying to synchronize. They also contain some memory barriers, which define the guarantees of what memory is propagated, which I'll go through in a little while. But the key thing here is that they're a single point in time. It sort of operates on all the stuff that came before it with all the stuff that will come after it. So you go draw, pipeline barrier, draw, then it means that you've got that first draw as a synchronization dependency with the second draw. Events are quite similar. They basically do the same exact job, except they operate over a range. And what that means is that you'll do a set at some point in time and a wait later. Anything in the middle of that is not interfered with by that synchronization. So you would synchronize all the stuff before the set with all the stuff after the wait. And anything in between basically gives you an opportunity for additional overlap. There is also the ability to have some sort of CPU interaction, so you can set and check the status of an event on the CPU, which can be useful for certain cases. I would warn you against doing this too frequently. There's a good chance that an implementation has a semi-invisible timeout. So if you wait too long before setting your event after submitting it, it might just time out your device and you lose everything. In most cases, you can just defer your queue submit until you're ready to actually start the work. But there is a small set of use cases where it's actually applicable. So the difference between the two is, well, or rather when you should use each. The pipeline barrier, you should definitely use it if it's for point synchronization. If you're synchronizing stuff before one point and after another point, then you should use a pipeline barrier. It tends to be cheaper to do that with a pipeline barrier than squishing an event with nothing between it. On the flip side, if you actually have some work you can do in the middle that doesn't depend on either of those bits, you should use an event because that gives you more opportunity for overlap. If you are going to use events for CPU, GPU synchronization, the main thing that it's going to be useful for is if you have memory access between the processors and you're trying to do very late latching of the data to reduce latency. There are potentially some VR use cases for this, for instance, but it's not a step you should start on. It's just there if you do need it later. So memory barriers, I promised to come back to them. The main thing here, if you think back to my memory space diagram, I had those 3 levels. Memory barriers, they operate between the cache levels and the VRAM level. The other bits, the CPU to host visible, is handled by API commands, and the shader stuff to the device visible is handled by SPIR-V instructions. So there's 3 types, as I said. The first of these is a global memory barrier. This is the simplest. It basically just means that any memory that was accessed in the way that you've specified will have some sort of guarantee. So the source access mask basically says accesses of this type will be propagated to device memory, and then the ones in the destination access mask will be propagated from device memory to that access mask. You can sort of think about it like flushing and invalidating entire caches at once. And this is usually what you would use unless you have specific things to do with a particular resource. There are resource-specific ones, which I'll go through in a second, but for the most part, you should use global because otherwise you may just end up flushing the entire cache multiple times or doing unnecessary small flushes. And the main thing here is that you do have to define the prior access, so the source and the destination access must specify because you are telling it which spaces to propagate from and to. So the first resource-specific barrier is a buffer barrier. So this will take the access types as before, but it also adds a buffer range, which says this area of this buffer, any writes to this region of that buffer is what I want to propagate in whichever direction that you specified. And then there's also this idea of queue ownership. Ownership's a little strange. I'm not going to go into it too much now, but basically it defines what is allowed to access. It may involve some sort of memory layout changes under the hood for certain resources, but for the most part, you can just think about it as allowable queue families which can access a write. I meant to say, sorry. So for the ownership transfer, you do, again, as with the access masks, you say what the source queue family was and what the destination queue family was, so it knows exactly where it's propagating. Image barrier is another step up, very similar to the buffer memory barrier, same information except for an image. But there's also, images are slightly more complicated than just a raw buffer. A raw buffer is just treated as linear memory for the most part. Images have all sorts of strange access patterns, and a lot of implementations have image GPU compression. So they might have a fast way to write out from their fragment shader and compress that data as it goes along, which enables them to save a lot of bandwidth. And in order for them to use that, they need to know how you're actually accessing the data at any given point. So again, you've got an old and a new, which is sort of like source and dest. You say what it was used for before and what it's about to be used for. There's lots of different ones. So there's one for color attachment rights. There's one for transfer source and destination, and some other ones. If you do find yourself switching too frequently, there is a general one as well which you can use, and I would advise using that if you find yourself switching more than maybe 3 or 4 times, because each switch could incur a decompression or compression of data. So if you're going to do it a lot, general is there for that. So a slightly complicated example. I did have to try quite hard to squeeze this onto a single slide, as you can see. But I'll go top to bottom, and you can sort of see what it's doing. So we'll start by assuming that the buffer we're going to write has already been mapped. You've already mapped the memory for it. And we've got an image that we're going to try and upload to the GPU. So the way to do this in Vulkan overall is to upload the linear image that you've got on disk into a buffer, and then copy that buffer to a tiled image, which will get it into the tiled state, which I think Michael mentioned earlier about doing tiling via copies. So if you read that linear image data into a buffer, so I'm just using fread here, fairly straightforward, and then it's being flushed, as I said before, with the flush command, which will take it from the host to the host visible memory space. After it's there, we now need to set up some sort of pipeline barrier, some synchronization primitive in order to get it into a place we want it to be, which is namely the GPU. So we'll set up the access masks on the buffer, and we know that we've just written it via the host, so that's the first access mask. And we know the place we want it to go is a place where the GPU can read it for the copy. So that's what we've set up there. Then we've also got an image that we want to copy to. In this case, there is no prior access. We've just created the thing. There's nothing going on in it. We don't really care what's happened. Just this is the first task. So we can say that. We say there's no prior access for the access type, and there was no old layout because we haven't set one yet. But then for the destination, very similar story as the buffer. We need to write to that from a transfer. So we set that that's the access type and also the layout. Both, they match up. And once we've all set that up, we can then do a command pipeline barrier, which can go to the GPU. And again, the stages I'm using will match the access types I'm using. So host stage for the read of the write of the buffer, and then transfer stage for the actual copy operation. Once that's been submitted, if we submit something after that, like the copy, it will guarantee that it's in those memory spaces. So we've done that. We've done a command pipeline barrier and a copy buffer front to image to copy that data across. And all other synchronization is taken care of because we've set everything up correctly. If you didn't do that, who knows what will happen. After we've done that, in order to actually use it for the purpose we want the image for, namely sampling in a fragment shader, so this is roughly mirroring the memory space thing I had before, we then need to do another pipeline barrier to get it from one to the other. It's not just as simple as it's on the GPU. There are multiple processors, multiple caches, all sorts of things going on. So you need to now transition it to the right place. So here, what we've done is we've said, well, it was just accessed as a transfer write, so we've set that. That's what it was. And what it's going to be is it's going to be in shader read, because we're going to sample from it. So for the access types, again, you can think of it like propagating from the transfer memory space, one of those device visible memory spaces, back up to device memory, and then back down again into the shader read device visible memory space. And from there, SPIRV instructions, like the sample instructions, will be able to read it and pull it into the shader itself. Now, that's sort of a deep dive into how fine-grained synchronization works, but actually, pipeline barrier operations, a lot of them you can get around not doing. I mean, the specific example, yes, you kind of do need them. But usually a lot of stuff can be handled with render passes, so I promised I'd talk about these. I'm not going to go into huge detail about them, but as they pertain to synchronization, I will describe them. What they are is basically a dependency graph. You set up a bunch of operations up front, say that I'm going to have all my drawers in my scene have this sort of structure about them with these dependencies between them. So that's something you set up at initialization time. And then when you come to draw, the driver already knows what's actually going to roughly happen. It doesn't know the exact draws because that's what you set up with the command buffer, but it does know that, you know, these are the sort of things I'm going to be able to overlap. And that usually gives opportunities to do things that otherwise you wouldn't be able to do. There's a lot of various driver and implementation tasks that need taken care of, cache flushing, clearing images, things like these, and they can all be pre-planned by creating a render pass. So render pass's main synchronization thing is this subpass dependency. A render pass is constructed from a number of subpasses. Each subpass has its own drawers, and then you set dependencies between those subpasses. You can look at this. It's got similar information to the pipeline barrier, and it's explicit between two subpasses within a render pass. You should probably ask at this point, does anyone not understand what I'm vaguely getting at with a render pass? Does anyone need a bit more explanation, or are you all okay? Because I kind of banked on someone else describing them more fully before I got here, so yeah, okay, well, you can always ask afterwards. So anything that's in an attachment, as in you've put it on your frame buffer and it's referenced by the render pass, the memory barriers are sort of implicit. It's got enough information within how they're used in the subpasses, in the ordering the driver selects, to make sure that all the attachments are in the right place at the right time. But if you want to do something like write a buffer and then read it in a later subpass, you can do that, but you need to set the access masks here in order to do that and set a dependency between them. You do need to set the rest of the subpass dependency for the attachment, so that's quite important, just not the memory barrier. One thing that is actually present in the other two synchronization types as well, but is mostly important here, is the idea of a frame buffer local dependency. So if you know that the dependency you're setting up between two subpasses is such that fragment at location xy is going to write a value, and then the fragment at the same location xy in a second subpass is going to read that value, and there's no scatter or gather operations between them, you can set that there's this VK dependency by region bit, which basically says, I am pixel local, I don't need to synchronize the entirety of that subpass with the entirety of this subpass. And that gives a huge opportunity for implementations to reduce how much work that is. Particularly on mobile, it's very important, but even on desktop, this gives them some sort of win on some hardware at least. Now, I did say between two subpasses, that subpass, but they can both be the same. So yeah, a little bit sketchy, but yes, that is one thing you can do with them. And that actually allows you to put a pipeline barrier in a subpass. So this is for things like order-independent transparency. There's sort of a spec bug at the moment, which doesn't quite let you do that, but if you wanted to do some things, you can. The key thing here is you can't do backwards progress. You have to do forward. So you can't have one stage wait on a later stage in a previous draw. So you can't say make it so the vertex stage or in draw 2 waits on the fragment stage in draw 1. That's just not allowed. You could do that between subpasses, but not within a subpass. And if you do have any fragment stages in there, you have to make sure you use the dependency by region bit, which is why I introduced it. This is basically to make certain guarantees about what can go in a subpass when the driver does its planning step when you create it. And yep, there's one more thing. You can also make one of those subpasses actually not really a subpass, but rather stuff that happened outside the render pass, so either stuff before or stuff after. The idea here is that it gives you the ability to say like this subpass doesn't really depend on anything, or to say explicitly that it does depend on something and that happened outside the render pass. One common dependency is to have a layout transition between presentable to renderable, which you're going to be doing pretty much every frame if you're rendering to a Windows system. And the sort of naive approach to do this is with a pipeline barrier right before you do the render pass. But in actual fact, you can set up an external dependency via this with the same parameters, and it will just do that for you as part of the render pass with more control for the driver in terms of being able to plan where it goes, and it tends to be more efficient. Right, so speaking of that, so I've covered half this here. I'll have to talk about semaphores to fully complete this picture, but I think Carl talked some about this. So if you want to acquire image, right, so for just quick summary of WSI, Windows system and stuff, the idea is you have a swap chain, you acquire an image from the swap chain, you then render that image, and then you present that image back to the presentation engine. So there's 3 distinct stages, and there's a specific layout for an image for presentation, which is present source. So what you can do is you can set up a subpass external dependency, well, 2 really, that tell your driver for your Vulkan implementation what transitions to do and in what order. So you could, again, do this with a pipeline, but it won't be as efficient. Bit I'm not showing you here is within the render pass, you have these 3 parameters, which is initial layout, final layout, and the layout used on any given subpass for any given attachment. In combination with those layouts and these subpass external dependencies on the screen, that gives the driver all the information he needs to do the transitions. So what you would do is you set your initial layout to present source, so that will come in and it knows that's what is there. You'd set your subpass to be renderable, and then you'd set your final layout to be present source. In order to actually make sure that they happen at the right time, you then have to add the subpass dependency. That was a better way to describe it. So what you've got here is the first one is an external dependency on stuff that happens before the subpass. By saying subpass external on source, it means stuff before the render pass. You'll then put the first subpass that's used in as your first dependency, as your destination subpass, and you'll then add the relevant pipeline stages. Interestingly, you don't really care too much about the source pipeline stage in this one because you already have to guarantee that you've used a semaphore between the acquire and the actual submit, which I'll go into in a minute. So you can just say top of pipe here, which just basically means this command has been submitted. But for the output, the destination, you do need to say, well, I'm going to write this as part of the render pass, so my destination stage mask is the stage which writes to the color attachment. Similar story for this access and destination masks. Don't care about the previous access because it's already guaranteed, but the output color attachment write bit needs to be set. And then you've basically got the mirror of that on the other end. You say the last subpass is used in, and you put the destination subpass as external, which means, again, everything outside the subpass after it. Similar story here. Set the source stage as the output stage, and the access mask as the output write. And again, for the destination, don't care because, again, you have to have a semaphore between the submit and the present, which makes these guarantees for you, which will make more sense once I've described semaphores. So semaphores are used to describe queues. These are my first course synchronization primitive. Now, these are not necessarily if you're just doing stuff on the single queue with some exceptions. If you are using the presentation, it is kind of an exception, even though you might have a queue family that supports both rendering and presentation, the operations are distinct. So if you're doing submit, 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 you don't need them. But if you're doing submit, present, submit, you would need them. So it's sort of more tied to the queue command that you're using. But they are fairly coarse. You basically these are a set of command buffers. I'm going to submit them with one or more semaphores, and it won't do any synchronization within those command buffers, just across all of those command buffers. You rely on the stuff I've already talked about for the within command buffer. They do imply some implicit memory dependencies, which is why we had all that stuff before saying don't care. So they will basically propagate all writes between any of the device visible memory stages and the device memory, which basically means that a lot of pipeline barriers can be ignored because you've already guaranteed them with the semaphore. They do not guarantee any visibility to the host, though, so if you need to do that, if you need to transfer data back and forth, you do need to use a pipeline barrier, like for the texture upload case. So quickly going back to acquire, render, present, there is more information. There's quite a lot of it. When you do an acquire, there's only a couple of bits that are actually relevant here. When you do an acquire to get an image from a swap chain, you actually give it a semaphore, and that semaphore will indicate, or it will signal when the image has actually been acquired. It's more of a kick some work off, wait for you don't wait on the CPU for that acquire to happen. It will just happen at some point, and you'll get notified by this semaphore signal. So then when you submit your command buffers with that render pass that I talked about a minute ago, you add this acquire semaphore into your submit so that that submit will wait for that image to be acquired before trying to do anything. And then you'll signal that at the end, so you add another semaphore to that batch that will be signaled once that graphics work's complete. Again, there's no CPU interaction here. This is all pipelined. You'll submit that work, and then at the end, after that, you will then submit a present. And again, present is pipelined. You don't want to wait for that CPU, for that queue submit to finish on the queue submit. You don't want to wait for the queue submit to finish on the CPU. So again, you take that graphics semaphore you've already set up and you pass it to present, and then we'll just start executing, but it won't really actually do anything until that semaphore signals. There is, of course, one way, which Carl already mentioned, to get synchronization back to the CPU directly, which is the fence. So this is very coarse-grained, even more so than the semaphore, because you only get one per submit or present or acquire command. The idea being that it's only useful for certain cases, but those cases are very important. So it's got the same implicit memory dependencies as semaphore. If you see it's complete, it has propagated all writes between those device memory spaces, and again, does not have any visibility on the host, despite the fact that you actually have to wait on the host for it. It does not guarantee any memory visibility to the host. You still would need a pipeline barrier event for that. Oh, that's right. I took out some slides because I didn't think I had time, but it turns out I do have time. So we'll just quickly go to that one. Okay, so the main use case for fences is that is for multi-buffering. The idea being that once you've submitted 3 frames, you can then check and see if that first one's done. It's usually possible to, as long as your scenes are fairly stable from frame to frame, which typically they are, you can sort of say, well, I've submitted 3 frames. I know the GPU will probably be done by now. So if you've set up 3 instances of all your resources, then you can wait on that fence after that third one finishes, and before you start reclaiming the resources that would have been used in the first frame, and you sort of keep doing this business where you reclaim ones that have been long completed because you know the GPU is no longer accessing them. And you can use one fence basically for all of your resources because you know that that giant packet of work is completed, and you don't really need any more granularity than that. You could use events if you really wanted to, but it's a little pointless, and fences are a lot more lightweight from that perspective. Very conveniently, the acquire next image when you're doing rendering to a Windows system actually provides you with an index you can use here. So if you've set your swap chain image, your swap chain size to be 3 images, then you know that if you just set 3 resources for all your multi-buffering, 3 sets of resources, you can just use that index for the whole thing every frame, which makes things quite simple. All the way back. Right, okay. So there is more synchronization in Vulkan. That is quite important. It's sort of implicit, but not really, which is a strange thing to say. The first one of these is QSubmit, which is probably the most important piece of synchronization in Vulkan, because without QSubmit, you can't do any work. You can record as many command buffers as you like, but until you submit them, no GP work's going to occur. And they also have guaranteed forward progress. So once you actually submit something, you don't have to prod it anymore to ensure it completes. As long as you haven't set up some invalid state or some infinite loop in a shader, which is invalid state 2, it will finish at some point in finite time. You would need a fence to figure out when that was, but it will complete. They do also have an implicit memory dependency. So whenever you do a submit, any writes that have been done and propagated to the host visible memory space will propagate through the device memory and through to the device visible memory spaces, which makes it quite convenient. So if you write some buffer, flush it to host visible, then you know that any commands submitted with that submit will be able to see that on the device. And that's another place where you can kind of avoid some pipeline barriers. The other one, and this has only got really one sort of use case, really, one legitimate one, I think, well, maybe 2, is wait idle. You can kind of think of this like GL finish from OpenGL. It's extremely heavyweight. It waits on the CPU for all execution to complete, either on a single queue with queue wait idle, or for the entire device with device wait idle. Don't use these except when you're doing teardown. At the end of rendering, when you know that the user's hit quit and you just want to wait until they've finished, the GPU's finished doing whatever it's still doing, that's perfect for these. If you start putting these between frames, you're just introducing serialization. That's sort of first CPU, then GPU, CPU, then GPU serialization ahead at the start. because they will guarantee that no overlap. But they are very useful for teardown, and the other sort of legitimate one is for debugging. If you can't figure something out and you think it might be synchronization, but you shouldn't ship with it for that. Oop, wrong way. Am I one slide? What the? Okay, I'm on the right slide now. So that boils down to a few rough programmer guidelines. I also struggled to get these on one slide, but I've done it somehow. The key thing, which is kind of annoying, is you have to specify exactly the right amount of synchronization, not too much, because if you do too much, you introduce stalls, and if you do too little, then things will go wrong, which is a pretty daunting task if you're coming at Vulkan from an OpenGL or older API background where everything's reference tracked for you. But the validation layers will help. They can catch quite a lot. They won't catch everything yet, but they are improving over time, and certainly they'll get some of the more common issues. Within the synchronization stuff themselves, do pay attention to the pipeline stages you're asking for. Think about your image layouts, because if you get them right, you can really hit a sweet spot of performance. Do prefer render passes for your synchronization. They give the driver an opportunity to pre-plan stuff that you wouldn't otherwise get with the manual pipeline barriers and events. And do pay attention to any implicit dependencies. There's no point flushing all your caches if you know that a Semaphore's already guaranteed that that happened. So you don't want to do more unnecessary work than is needed. And unfortunately, at least in the lieu of the validation layers being perfect, you will get some different behavior depending on implementation. That sort of problem of not seeing any errors I talked about before. You might find that whatever your development platform is, oh, look, it all works great, but then you push it to some other platform and suddenly everything blows up in your face. So it's useful to test and tune, but that's always been true of graphics programming anyway. In summary, keep your GPU fed without getting bitten. Does anyone have any questions? No. Oh, Angela's got the microphone.
Hey, so you explicitly called out that that a submit guarantees propagation to device-readable memory.
Yes.
For copies and such. Does that mean that you're recommending using a separate command buffer for copies, for copy operations, so that you don't have to do that, all that synchronization yourself?
Hang on. Right. Well, I think what I'm saying is sort of. I'm kind of right. So in that first example, so it was a bit misleading. Let's go back to that a second, because I think that's probably the easiest way to illustrate what my point was. So my very first example, which is somewhere back here, texture upload. Okay. So I was technically over-synchronizing here. So I've put in host write bit, and I've put in some stuff about waiting on the host. You don't actually need to do that bit. You could take out the host write bit in the access mask and turn it to 0, and you could take out the host bit there as well from the pipeline barrier and put it to top of pipe. Because realistically, when you submit, that's already guaranteed. It's specifically that bit of synchronization. In fact, actually, maybe the only bit that's relevant of that pipeline barrier is realistically is the layout for the image. The rest of it's all guaranteed by submit anyway. So you don't have to handle the writes and you don't have to handle any of that, because you know that anything you've written to that host visible space has already gone over. The exception to this, which is when this would become relevant, is if you were using events that you were setting on the CPU. So if you had already submitted the work and then you needed to wait on the event, you would put all this information in that wait event so that when you set the event on the CPU, it would actually make sure it happened then instead. But if you're just doing submit, you don't need any of that. Hopefully that made sense. Any other questions? Oh, there's one here.
It's probably just a newbie question if we have time. Back to that last example where you had the VK flush mapping memory thing at the top there.
Right, yeah, the texture.
I was just curious what exactly that does. Is that a handle to memory that's already host visible at that point and the FREAD is copying that directly in there? Or is it the flush memory is actually forcing a copy to occur at that point in time?
Okay, actually let's go back a little bit more further back to my memory space diagram. It's probably the easiest place to do it. Right back to the start of my slide deck. Wow, really far back. There we go, okay. So when you do that, the fread in that example, when you basically do your mem copy, whatever else, it's guaranteeing that it's there in the sort of processor register space. Obviously, your CPU might guarantee, memory model might guarantee it's in some sort of cache as well, but from the purpose of Vulkan, doesn't really matter. That cache is just wrapped up in this bottom level, what I've vaguely called processor register space. In order to get it to the host visible, that's when you need the flush. The flush will do that. It will take it from that bottom level host area memory space and push it to what Vulkan considers the host visible. And the reason I've been kind of vague about what this actually maps to is because that might actually just be CPU RAM, because then that might just get copied through to VRAM on a discrete card, for instance, or it might be some special area of VRAM on a discrete card. It could be anything. The actual mapping is implementation defined. We just made sure we had enough information to map it as we felt reasonable. Does that answer your question?
So it's efficient if that's possible on that platform? Or is it?
So you need the flush. So the thing that the flush gives you is it guarantees that you've definitely got through there. So these memory spaces, they don't necessarily exist. It might be that, say, you've got a UMA system with no caches, right, which are very rare in reality except for FPGAs. But like I said, a flush doesn't actually force the flush to happen. It just means that after that flush has happened, you can guarantee it has happened. So it's all about making guarantees and not actually forcing an operation to occur. So if you don't need to do that step on your implementation, that flush will do nothing. It's a no-op. But if you do, then it's an opportunity to actually use it. I think what you'll find in practice is that a UMA system will probably skip that host visible area and just go straight to device memory, but it's more wishy-washy than that. But in order to actually guarantee that everything occurs, you just specify everything, and the implementation will no-op out wherever it doesn't need to do.
So as you mentioned, a lot of the time applications will work even if we get the synchronization incorrect.
Correct, yes.
And sometimes there are implicit operations that, implicit synchronization that means that we don't have to explicitly synchronize it. So I guess I'm just wondering, are there any good tools or methods that we should be using to test the correctness of our programs?
Well, the only tool that really is useful at the moment is the validation layers. I am not 100% sure how much they test. I know they do catch some stuff. I know for layout transitions, for instance, I'm pretty sure they're quite sharp on that. I think there's some amount of validation for other bits as well, but I haven't checked exactly what's there. I know some validation of, well, there's certainly bugs out for validation of things that shouldn't happen as well. So if you over-synchronize, I've at least posted some bugs to get that detected as well. But if you run into a synchronization bug and find that the validation layers aren't catching them, that's, file a bug for it, because that should catch it. I'm not sure which layer that actually equates to, but they were all in one repository anyway. So you just file a bug there and they'll figure out where to put it, and hopefully you'll get some good discussion about why and what and where it should be.
My hat's off to Tobias for taking the hardest topic in Vulkan, I think, in my view. I did talk early on about how part of the big challenge for us taking Mantle and turning it into Vulkan was to make it hardware independent. So you hear what you hear when you hear Tobias talk about this. Lots of, you have all of these stages that Vulkan says it's invalid behavior if you don't correctly express the dependencies. Not all hardware needs all of these, and there's probably no hardware that needs every single one of these. But there's at least one piece of hardware that does for each one of these. And so what we're asking you to do is express all of the constraints, even though some implementations don't need all of them, so that we can guarantee that on every machine you might ever run on, it'll be correct. Now, you may think, oh my God, I'm making the CPU do all this horrible work. And so Vulkan must be terribly inefficient. But of course, most of these, like these layout transitions and things, are happening as you put the command buffer together. And if the particular driver you're running on knows that it doesn't need something at this point, it's just gone and it won't go into the command buffer at all. So it's an interesting challenge, and we are still learning how to teach it, and we're still learning how to understand it ourselves.